We've already talked a little bit about kinetic energy, and now we're just going to try and come up with a formula to represent it and see how we can solve problems related to it. In general, remember that kinetic energy just means the energy that's possessed by any object due to its motion. And in general, we can also say that any work that's done to bring an object into motion will equal how much kinetic energy it has when it's in motion. And again, if we think of like an egg moving, think about how the splatter would compare if it was just moving at 2 meters per second compared to how much it would have if it was moving at 20 meters per second. So when things are moving at really high velocities, they can do more damage. And so that must mean that if they're moving at a greater velocity, they have more energy. Also, you can imagine if it was a much bigger object than an egg, something with a lot more mass, it would have even more ability to do damage. So we should expect that mass will have something to do with this as well. If we're going to try and actually come up with a formula, we can once again use the work-energy theorem. We can go back to our definition of work and see what that tells us about the amount of energy involved. So let's take a simple situation. Let's just imagine that we kick a soccer ball along the ground, which is going to cause it to accelerate from rest. And we're going to try and figure out how much energy we've given to the ball now that it's traveling at some speed. And that new speed it travels at, we're just going to call v. We don't even know how fast it's going, we'll just call it v. And again, however much energy we give to the ball when we kick it will be the amount of kinetic energy it has when it's moving. So let's think about this. Let's think about the work that we're doing. Well, we start with our basic formula that says that work is equal to force multiplied by displacement. It's the amount of force that I'm using to kick the ball multiplied by the displacement that it travels through as it's being kicked. And I can use that to find work. But remember, in this case, the work, well, that's a change in energy. And the change in energy is the amount of kinetic energy it'll gain. And so instead of calling it work is equal to force times displacement, I could say that the amount of kinetic energy that I'm actually looking for, which I'll call EK, E with the subscript K for kinetic, that is actually equal to my amount of force multiplied by my displacement. But remember that the amount of force that I'm applying, if I assume that all the forces were balanced initially and I'm applying some new force, that really means my force is like an F net. And so that means the force that I'm applying I could replace with ma, mass times acceleration. So I take that and I replace force with mass times acceleration. So now I arrive at this statement that my kinetic energy will be mass times acceleration multiplied by displacement. Now I can do another little mathematical trick, because what I've arrived at is MAD. And if I just focus on the last two, if I just focus on the acceleration times displacement part, AD, those variables are connected together in another important equation, one that we saw from our kinematics unit. It was this one here, the one that doesn't involve time. And in fact, if we rearrange the equation just to get the A and the D all by themselves, we end up with this little formula. We end up with the fact that A and D multiplied together is really the same as taking your VF squared, subtracting your VI squared, and dividing by 2. And here I'm just using F and I to mean the same thing as 2 and 1. It's like your final velocity, subtract your initial velocity, and then divide by 2. And so what we do then is we make a substitution and we can replace the AD with this great big bracket. And so instead of saying mass times A times D, it's really mass times this great big bracket that's equal to A times D. Then we can do a little bit of an expansion. So we would then multiply mass times each term inside of the bracket. And we end up with this statement here. Just a bit more of an expanded mathematical expression, but then we can even simplify it from there. Because remember, if in this case our initial velocity was 0, which we said at the start because the ball was starting from rest, that means this entire term that has initial velocity in it is going to become 0. So that entire thing will disappear. And this final velocity, this is just what we called v. It's just that velocity that it ends up having in the end. So instead of calling it VF or V final, we'll just call it V. So what I arrive at is this final statement that says that my kinetic energy that I've given to the ball is really just its mass times that new velocity squared, but also with this extra little factor of 1/2. Or you could also think of it as dividing by 2. And that just happened to pop up because of the mathematical strategies we used along the way. Now again, just like we did with the gravitational formula, I would never require you to derive this like I have on a test. You would just need to know how to use the kinetic energy formula that we arrived at. So now if we look at our final result, we can break down what each variable is really telling us and what units we need for it. So EK is that amount of kinetic energy that something has when it's in motion. And remember that it's going to be measured in joules. M is just mass, and we'll keep that in kilograms so that it fits well with joules. And velocity we'll keep in meters per second, again, so it fits well with this idea of joules. And we can do a little bit of unit analysis just to prove that. We know that in the end, our final answer should be in joules. That's what kinetic energy needs to be measured in because it's a form of energy. And then we multiply 1/2, which has no unit, so I won't even write it. We multiply that by mass, which has units of kilograms. And then we also multiply by velocity, which has meters per second, but then that entire unit gets squared. So really that means I'm taking kilograms and multiplying by meters squared per second squared. When I square meters per second, that means I have to square the top of that unit and the bottom of that unit. So I get kilograms being multiplied by meters squared per second squared. If I just kind of stick that all together into one common unit, kilograms times meters squared per second squared, well, that's exactly the same as a joule. So I arrive back at what I should get in the first place. So we're still getting joules, even though we're doing it in a very different way to the way we did it with the original work formula, and even different than the way we did it with the gravitational potential energy formula. So all three of those formulas, the work, the gravitational potential energy, and the kinetic energy formula, they all produce joules. They all produce the correct units, even though the variables involved are all very different. But the most important thing is to now take that formula that we've derived and to be able to use it to help solve some problems. So obviously the first thing we might try and do with it is to actually find how much kinetic energy something has. So let's take a situation of a pitcher on the Blue Jays, and they're throwing a baseball that has a mass of 146.1 grams. But before I do anything with that, I'm going to divide that number by 1,000 so that I can convert it into kilograms. So I actually want to keep it as 0.1461 kilograms. I'm also told that the ball is being thrown with a velocity of 45 meters per second. That's how fast it moves. And for the record, that's approximately 100 miles per hour. That's roughly what the fastest pitchers in baseball can throw. And I'm looking to find EK, kinetic energy. That's my required information. So in this case, if I just write down my original formula, it's actually already set up to find kinetic energy. So I can plug into it directly. The 1/2 is still just a 1/2. I plug in my mass, making sure that it's in kilograms, 0.1461 kilograms. I multiply by 45 meters per second, but then that value gets squared. And when you punch all of that into your calculator, you should get 147.926 and some other stuff. But when we round that off to just 2 significant digits, it's about 150 joules of energy. And then we would just write a therefore statement to summarize that. We can also remember that this equation isn't just used for finding kinetic energy, because sometimes we might already know how much kinetic energy something has, and we're trying to find something else about it. So in this case, let's say from some other measurements, we know that a tank shell, which is 25 kilograms, has a kinetic energy of 3.7 times 10 to the 7 joules. So that's a lot of joules of energy. And we want to know how fast it's traveling. And we can use our same formula to do that. But again, we still state givens and requireds. In this case, our mass is already in kilograms, so we can leave it as is. Our kinetic energy is 3.7 times 10 to the 7 joules. And now we're looking for velocity in this case. How fast is it going? Give ourselves some room to work. We can start with the exact same formula that we're used to. But if I want to find v, I want to start working and rearranging this equation to get v all by itself. Well, a few steps I could do, but the first one I'm going to try and do is multiply both sides by 2. And that gets rid of the multiplying by 1/2 on the one side. So I could say that 2 multiplied by ek is equal to mv squared. I can also divide both sides of the equation by m. Or in other words, 2 times ek over m is equal to v squared. If I want to write this in one overall summarized way, well, first of all, I'm just going to put the v on the left side. But then what I end up with on the right would be just square root of 2 multiplied by ek divided by m. And just be careful, I kind of got a little bit underneath, but remember that we are square rooting this entire thing. So let's plug in what we know. It's going to be 2 multiplied by 3.7 times 10 to the 7 joules divided by 25 kilograms, and then we're going to square root that entire thing. When you do that, you get about 1720.46, and it kind of goes on from there. But then if we round this off, we want to round again to 2 sig digs, so it's about 1700 meters per second. So it's an extremely fast-moving shell. 1700 meters per second is what we found. And of course, we'd still state a final therefore statement to summarize this information that we found.